And hello everybody, here are your notes for curvature of a function. So it's called concavity, points of inflection, and the second derivative test. So we're going to be using the second derivative, f double prime, to determine what the curvature or concavity is on original function f. So the big idea is if f is f double prime is a positive value, then original function f is concave up. If f double prime is a negative value, then original function f is concave down. So this is kind of the big idea. We'll talk about why and how to go through the detailed test to determine whether it's concave up or concave down. But essentially what we're looking for is the sign value on f double prime. So just like when we did the first derivative test, if f single prime was positive, then f was going up. If f single prime was negative, it was going down. For this one, we're going to be using the second derivative to determine what the curvature is, concave up or concave down. And let's go ahead and just quickly kind of look at why this is the case, and then we'll get right into the notes. So if we look at some curve that is both concave up and concave down, so there's a concave down section of the curve. Right about here, we're going to start to change the curvature and switch it to concave up. So we're going to switch it to concave up on this portion of the curve. So that's our original function f of x. And to see why the second derivative is going to tell us about the curvature of the graph, let's first kind of look at the slopes on certain portions of the graph. So let's look at the slope of the tangent lines on the concave down section. So here, notice we have a pretty steep positive slope. So if you were looking at your f prime value, and we'll just kind of make up some hypothetical numbers here. So let's say f prime was going to give you a value of 6. So let's say f prime is 6. So that's saying that the slope on function f has a positive slope of 6. But as you move along the curve, if I looked at a slope here, and then here, and then here, and then right at the top here, and then here, and here, and if we think about kind of the hypothetical slope values, you know, this is a steep positive slope of 6, this might be 4, this might be 3, this might be 2 or 1, this is obviously 0 right at the top, and then you get into some negative slopes. So maybe -1, -2, because it's steeper and going down, -3. So if we look at the pattern of the numbers, f prime is going to have values of 6, then 4, then 3. Again, these are all hypothetical numbers. Then 2, then 0, then -1, -2, -3. So if you look at the values on f single prime, the first derivative, notice the values are decreasing. And we talked about yesterday the first derivative test. The first derivative test can tell you if a function is increasing or decreasing. So it looks like f single prime is decreasing. So which function would talk about the increasing or decreasing behavior of f single prime? That would be its derivative, f double prime. So if f single prime is decreasing, then that means that f double prime, its derivative, would need to be a negative value to say that f single prime is decreasing. So all these values on f single prime are decreasing, so the second derivative would be negative, and then if you look at the curvature of the original function f of x, the curvature is concave down. So in summary, if f double prime is negative, So if f double prime is negative, then f must be concave down. And then it kind of works the other way. If you looked at the slope values on the concave up section, so notice you're going to have a negative slope, and then another negative slope, but not quite as negative, then a zero slope, then a slightly positive slope, and then a bigger positive slope, and a bigger positive slope, and a bigger positive slope. So if we thought about some hypothetical numbers for the slope values, this could be maybe -2 or 3, -1, 0, 1, 2, 3, 4. So if you notice the pattern of the numbers, they're going from negative to positive, so they're increasing. So f single prime is increasing, therefore f double prime must be positive. And notice when f double prime is positive, original function f is concave up on that portion of the curve. So that's going to be concave up versus concave down. And you don't really need to remember all of the workings behind it. You just need to realize that when f double prime is negative, f is concave down. When f double prime is positive, f is concave up. So let's go ahead and take a look at your notes. So this here is just reiterating what we just talked about. F is going to be considered concave up if f single prime is increasing and the tangent lines are below the curve, therefore f double prime must be positive, so we can put a note in that f double prime would be positive in value, and f is concave down if f double prime is negative in value. And again, f double prime being positive is speaking about this right here. If f single prime is increasing, then f double prime would be positive, and if f single prime is decreasing, then f double prime would have to be negative. And just like yesterday when we did a first derivative test, for this one we're going to do a second derivative test. It's going to be the same idea. We're going to do an interval test. We're going to find our possible curvature changes. So this is what they call points of inflection. And more specifically, they are potential points of inflection. You do actually have to have a curvature change for it to be considered a point of inflection. So you're going to find all the potential points of inflection. That's going to be where f double prime is 0. So where f double prime is 0. And then you'll test numbers in that interval from a to b. And you'll choose a test value within this interval, some number, and see what the value is on f double prime. And if f double prime is positive, then function f would have to be concave up. If f double prime is negative, then function f would have to be concave down. And a point of inflection is where the curvature changes. So all these are points of inflection because the curvature changes, but if, for example, let's say maybe it was positive on this one, and then let's say maybe it was positive again, then it would be concave up. This C sub 3 would not be considered a point of inflection because that was not a change in curvature. And again, there's the part in your notes where they talk about a point of inflection being a change in curvature. This part of the notes, this will come up later on in the practice, but this is just another way to use the second derivative test to not determine the curvature of a function, but to determine the extrema. So we were using critical numbers in the first derivative test to determine the extrema. You can also do it with a second derivative. The reason being is if you know your possible extrema occur where f single prime is 0 or undefined, and those are going to be the critical values. So the critical values being where you could have a change in increasing or decreasing behavior. If you just take your critical value and plug it into the second derivative, so we're going to put a critical value right into the second derivative. If, for example, you got a result of a positive number, well, that's telling you that at this critical value, this possible min or max, is telling you what the curvature is there. So if it's concave up, and this is a potential min or max, then if it's concave up, then we can kind of deduce that that's going to have to be a min. So that's going to be a min. And if when you put in your critical value, if you do f double prime of a critical value again, a different one, and let's say it was a negative result, then that's saying that the graph is concave down. So right at that critical value, it must be at a max. So we can tell whether it's a min or a max just by looking at the curvature. But the key is you need to remember that what you're putting into the second derivative is a critical value where you can have a potential min or a max. And then the last part would be is if you put in your critical value and you end up with a 0, it's not telling you whether it's concave up or concave down, then something else is happening in the graph there, so we consider that a test fails. We can't really determine if it's a min or a max, so we would need to go look at more information on the function. And this next section is gonna walk you through using the same function but using different techniques to find information on this function. And we're actually not going to be talking about curvature on this one. We're going to be talking about what we were talking about in some earlier units, finding a relative min or max, a relative extrema. And they want you to do this by just using the first derivative test. So first derivative test, we're going to need a first derivative. So we'll say f prime, and we will take the derivative. So again, taking the first derivative, so the 5 is going to come down, that's going to be a negative 15x to the 4th plus 15x squared. We're looking for critical values since we're looking for potential mins and maxes, so we'll set that equal to 0 to find our critical values. So we'll factor out a negative 15x squared. And it looks like a x squared minus 1 is left behind. Check it with multiplication. Distribute negative 15x squared back in. That's negative 15x to the 4th plus 15x squared. The x squared minus 1, you can factor that as a difference of two perfect squares. So x plus 1 and x minus 1. And our zeros are going to be when x is 0, because 0 squared would get us 0. When x is negative 1, and when x is 1. And then we'll go ahead and do a first derivative test. So we have 3 critical points to investigate: negative 1, 0, and 1. And we'll work on the whole interval from negative infinity to infinity. And let's see, let's look at f prime, and that will tell us what's happening on f. So we're going to test a number somewhere between negative infinity and negative 1. So if we put negative, let's say negative 2, back into the, I usually use the factored form because you can just keep track of the sign on each factor. So if I put a negative 2 back into this particular form, negative 2 going into the square is going to make it positive, and then a positive times negative 15 is a negative number. And then if I put negative 2 into the second factor, you're going to get negative 2 plus 1, so that's going to be a negative number. And then if I put negative 2 into the third factor, you're going to get a negative number. And a negative times a negative, that's going to get us a positive, and then that positive times another negative is negative. So the overall sign on f single prime is going to be negative, which means f was decreasing. And then we will test another number. So let's test something in this interval. So maybe a negative half you could think of. So if I put a negative into the first factor, the negative squared, that's going to make it positive. So this first factor is always going to be negative regardless of the number, since the square makes everything positive, and then you have a negative 15. So it's going to be negative on the first factor, and then positive on the second factor. So a negative half going in, negative half, and a positive 1. That's going to leave you with positive. And then into the third factor, if we put in a negative half, that's going to be negative. So a negative times a negative is a positive times another positive. The overall value is positive. So that's going to be increasing on function f. And then test another number. So maybe a positive half. So if we put a positive half in, we're going to get negative on the first factor. Put a positive half into the next factor. So that's going to be a positive. And then put a positive into that third factor. That's going to be a negative. So you get a negative times a negative, which is a positive, times another positive is overall positive on that interval. So again, f is increasing. And then if we do our last interval, so we'll test a number here. So if I put in like a 2, it's going to be negative on the first factor. It's going to be positive on the second factor, and positive on the third factor. So that's going to get us a positive times a positive, which is positive times a negative is negative, and that will tell us that f is decreasing. And from this first derivative test, we can determine what the extrema are. So that was the original question. So what are the mins and the maxes? So let's give ourselves a little bit of room. So looking at the function, it looks like it was decreasing and then it was increasing, where x is negative 1, so it was going down and then it changed and started going up. So that's going to be a min. If something goes down, then changes direction and starts going back up, that's creating a trough or a valley, so that's going to be a min at where x is negative 1. And if you want the complete ordered pair, so the x value where the minimum occurs is negative 1. If you want the actual minimum value, you're going to need to take the negative 1 and go find that y value. So negative 1 needs to go back into f prime, or not f prime, excuse me. Negative 1 needs to go back into f. If you put it into f prime, you would get 0 because we already solved that. So we want to know what the output is on f. So we're going to put that back into f. And if we substitute that back into original function f, you're going to get negative 2 for the y value. So that's going to be your min for your y value. So you're going to have a minimum at negative 1, comma negative 2. And then if we look at the next critical point where x is 0, it was increasing and then it kept increasing. So this isn't making a min or a max, this is just kind of slowing down. So the function was increasing, slowed down for a second, went flat, and then it kept increasing as it kept moving along the graph. So this is not going to make our min or max. This is going to be a place where it kind of flattened out for a second. And then the next critical value, it was increasing, and then it got to its critical value, and then it started decreasing. So that's going to make a max. and that's going to happen at where x is 1. And again, if you want to know the y value, the complete point, you're going to put that back into f. So put 1 into f, and you should get a value of 2. And you're going to have a maximum at 1, 2. And let's just go ahead and make sure we answered the question. So the question was, find the relative extrema. So final answer, we should have a min at -1, -2, and a maximum at 1, 2. Part B of this question, they want you to find the same thing. They want to know whether you have a min or a max, but they want you to use the second derivative test. So we're going to plug the critical values, the critical numbers, into the second derivative. So the critical numbers from part A, we already solved for that. So the critical numbers that we found from part A were x is -1, x was 0, and x was 1. Those were our critical numbers. And we're going to put those into the second derivative, so we're going to need a second derivative. So let me go grab the first derivative from the other page, and then we'll take the second derivative. So here's the first derivative from part A. I'm using the non-factored form since we're going to want to use our power rule to take the second derivative. So let's find f double prime. So f double prime, looks like our 4 is going to come down, and that's going to get us a -60 x to the third, and then bring the power of 2 down, so that's going to be a +30. Drop it down a power to the x. And what we're going to do is we're going to test our critical values into the second derivative and see what the curvature is. So we're going to do f double prime. What we're going to put into f double prime is one of our critical values. So we'll put in -1, one of the critical values. And when we put -1 into f double prime, we're going to see what the output is. So it's basically going to be a -60. -1 is going in to f double prime. And we need to see if that works out to be positive or negative. So if we do the calculations on that, we get a positive number. You technically get +30, but again, we're not really concerned about the number, just whether it's positive or negative. So it works out to be a positive result. So that's telling us that at this critical point, the graph is concave up. So if something is concave up, then it must be making a min. So again, we have a min at -1, which is what we determined on part A also. And then if you want to know where that min occurs or what y value that minimum is at, you want to plug that back into f, and you're going to get -2. So we're going to have a min at -1, -2. Same thing that we determined using the other technique when we did the first derivative test. Plug another critical number. So we'll put 0 in this time. That was our critical number. So put in a critical number. That's going to get us 0s and 0s. So that's going to get us 0. So this is going to be test fails. And if you remember in part A, we didn't have a min or a max at this critical number. The graph just slowed down and flattened out for a second. So test fails, there is no min or max there. And then if we plug in our third critical number, our third potential place where we could have a min or a max, put in your critical number and run that through the second derivative. So we're going to put in 1. And work the calculations on that. And you should get a negative number. So a negative number means that the graph is concave down. So at this particular critical number, It's concave down, therefore it must be making a peak or a max at where x is 1. And if you want to know what the y value is, the complete ordered pair, plug that back in to f. So put the value of 1 back into f. So if you do f of 1, then that should get you 2. So the y value on f, where that maximum occurs, is going to be at 2. So that is finding the same information as part A, where's the min and the max, but we used a different technique. We put the critical numbers into the second derivative to look at the curvature, and the curvature can also tell us whether we have a min or whether we have a max. And for this one, part C, we're doing the same thing. We're trying to find the mins and the maxes, the relative extrema on that function, negative 3x to the fifth plus 5x cubed, but we're using a different technique. The technique is to just use your graphing calculator. So let's say you didn't do any of the handwork, you didn't do any of the actual algebra behind it. You can just look at a graph of f prime. So you can just look at a graph of f prime and get all the information you need for a first derivative test. So just to recap, to get a graph of f prime, you want to put the original function into y1, and then in y2, you're going to ask it for the derivative. So to get your derivative command, you can go alpha f2 and find your derivative command, and you're going to take the derivative of y1. To find your y1 in the calculator, you can go alpha f4 and y1, and you're going to do it with respect to x. You're going to have to type an x in here, and for all values of x, so you're going to type an x in here. And if you just want to see a graph of f prime and not f at the same time, if you go to your equal sign, you can click on the equal sign and that will disengage it. So the one that is bold, notice this one is bold, it will graph y2 f prime, but it won't graph y1, the original function. And let's go ahead and look at a graph of this. So here's our graph of f prime. So I changed the viewing window a little bit on this, so it's not 10 in every direction. I think I put negative 3 to 3 on the x, just so we could see it a little bit better. So if you think about what you need for a first derivative test, you first need the critical values of f, which is where the first derivative is 0. So where is this first derivative 0? That's going to be here, here, and here. So you're going to get your first derivative, your critical number, at negative 1, 0, and 1. And let's go from negative infinity to infinity. If you were unsure on what those zeros were, you can trace it and type in negative 1 and confirm that it's a 0, or you can use your 0 feature on your graphing calculators. But we kind of already know that we're going to have critical numbers at negative 1, 0, and 1 since we did this by hand. And we're going to look for the sign on f single prime, and that's going to tell us what's happening on f. So remember, for the sign on f single prime, we're basically looking at its output values or its y values. So if we look at the graph, so from negative infinity until we get to negative 1, what are all the output values on the graph? So the output values are the y values. So if we look at the graph coming this way until we get to that first critical point, notice that all the outputs on the graph are all negative y values. So we're going to say f single prime is negative. And then if we look at the next portion of the graph, so if we look from here to here, all the y values are above the x-axis, so all your y values are positive. And then from here to here, all your y values are positive. And then when we look at the remainder of the graph from 1 to infinity, all your y values are negative. So if we look here, all your y values are below the x-axis, so you're going to get negative outputs on that portion of the function. And what does that tell us about f? It means f must be decreasing, increasing, increasing, and decreasing. Same information we got back in part A when we did it all by hand, but this was just kind of skipping over the algebra and just looking at a graph of f single prime. So if something is going down and then starts to go back up, then that must be making a min. So it's going to be making a min right here. And then if something is going up and then changes direction and starts going back down, then that must be making a max right here. So you have your min at -1, comma -2. Again, to find that -2, go plug that back into f. And, oops, plug the -1 back into f. Go plug the x value back into f. And that's going to get you a y value of -2. And for this one, the x value is 1. If I plug the 1 back into f, then we receive an output of 2, which we found in earlier parts. And then again, what's happening right here, you did have a critical number, but it didn't change its increasing or decreasing behavior. It looks like it kind of went flat for a second, and then it kept increasing after that. So yes, the slope was 0, but it didn't make a min or a max. So that is doing a first derivative test just by looking at a graph of f prime. And this next example is determine the points of inflection. So remember, points of inflection are where the curvature or the concavity changes. So this is going to be just a second derivative test. But they do want us to do it symbolically, so by hand. So we're going to need a second derivative. So finding f double prime, so let's find f prime first. So we'll look for f prime. Bring your 4 down, so it's going to get you 4x to the third. And bring the 3 down, so minus 12x squared. And that's the first derivative. We need a second derivative for the second derivative test, so we'll do f double prime. Bring your 3 down, that's going to get you 12x squared minus 24x. And for the second derivative test, it's pretty much like doing a first derivative test, just with the second derivative. So we still need to find where f double prime is 0 or undefined. These are going to be our possible points of inflection, so possible curvature changes. So we'll set this equal to 0. We'll factor out a 12x. And what's left behind is going to be an x minus 2. Double check your factors. 12x times x is 12x squared. 12x times the -2 is -24x. So your zeros for the second derivative are going to be x equals 0 and x equals 2. And we don't call these critical numbers. These are possible points of inflection. So these are our possible points of inflection. So possible curvature changes. And then we'll go do a second derivative test just like we did our first derivative test. So we'll set up a number line test. We'll test the whole interval from negative infinity to infinity. And our possible curvature changes can happen at 0 or at 2. And we'll look at f double prime and see what the sign is, plus or minus. So we're going to choose some test cases. So we'll choose a number somewhere between negative infinity and 0, maybe negative 1. If we put a negative 1 back into the factored form, so negative 1 going into this factor, that's going to be a negative. So that one's going to be negative. And if we put a negative 1 into this factor, that's going to be a negative 1 minus 2 more, so it's going to be negative. And a negative times a negative is going to be a positive. So a negative number on the first factor multiplied by a negative number on the second factor is positive. So what does that tell us about f? F must be concave up on the interval from negative infinity to 0. And if we test a number in this interval from 0 to 2, so maybe the number 1. So if I put 1 into the factored form, the first factor, 12 times 1, that's going to be a positive number. So that's going to be positive. It's positive. If you put a 1 into this one, that one's going to be negative. So a positive times a negative, that's going to be a negative. So that means f must be concave down. And then we're going to go ahead and test a number between 2 and infinity. So choose a number, maybe the number 3. So if I put 3 into the second derivative, you're going to get positive on the first factor, and you'll get a positive number on the second factor. So a positive times a positive is going to be positive, which means this is going to be concave up. So to finish this one up, we want to write our final answer in interval notation. You'll probably not see the second derivative chart like this in an answer key. So the interval from negative infinity, so we'll say from negative infinity until 0. So this is a comma b interval notation. So from negative infinity to 0, we said it was concave up. And from 0 to 2, we said it was concave down. And then from 2 to infinity, we said it was concave up. So that would be your final answer. And I know on the AP exam, if this was a AP class, on an AP exam, they don't consider your chart to be a final answer. So this would be your support work, but for a final answer, you want to put it into interval notation. And for part B, they want you to do a second derivative test using just a graph. So similar to what we did for a first derivative test, just by looking at the graph, we can do a second derivative test. The two key things you need for a second derivative test, you need to know where the second derivative is 0 or undefined. And we can get that off the graph. And you also need to know where the second derivative is positive or negative. And again, we could get that off of a graph of a second derivative. So to get a second derivative, we're on the calculator, we're going to do it similar to the first derivative. So your original function, you want to put it into y1. To get your first derivative, you're going to do what we did earlier, ask in y2 for the derivative of y1. So this is going to make f prime. So this is going to be f prime. So the derivative of y1. To get a second derivative, you're going to go to y3 and ask for the derivative of y2. So the derivative of y2 would be the second derivative of original function f. So y1 is f, y2 will end up being f prime, y3 will end up being f double prime, and then make a graph, and then from the graph we should be able to find this information just by looking at a graph. And here's the graph of f double prime. So this is y3 in our y equals menu. Be patient when you're graphing this. It does take a while. If you start hitting buttons too soon, then you're going to pause the graph, and it's never going to finish. So when it's graphing, you should see something happening over here. If you hit a button, it will put it on pause. If you hit a button again, it will unpause it. But it does take a while to graph, so you just need to be patient until it finally graphs the second derivative. So it takes a while because it has to figure out f, then f prime, then f double prime. So be patient when you are graphing these on the calculator. So what we need for a second derivative test, we first need to know where the second derivative is 0. So it looks like the second derivative is going to be 0 at where x is 0 and where x is 2. And again, if you're unsure of those values, trace them, see if they have an output of 0, or use your 0 feature. So we can set up our second derivative test. And it's going to be one of the possible points of inflection is 0, and then 2. And this is looking at the second derivative, and that's going to tell us about the curvature on function f. Remember, you're not looking at a picture of f right now. This is a picture of the second derivative of f. And the other bit of information we need for a second derivative test is where is the second derivative giving you positive outputs and where is it giving you negative outputs. So where does it have positive y values and where does it have negative y values. So from negative infinity until we get to 0, it looks like all the values on the graph. All the values on the graph are above the x-axis, so those are all positive y values. From 0 until we get to 2, all your values on the graph are below the x-axis, so those are all negative y values. And then from 2 to infinity, all the values on f double prime are positive y values. So that's going to be positive. So that tells us the curvature on f must be concave up, concave down, and then concave up. So same information that we got on part A, doing it by hand, just by looking at a graph of f double prime. So this is a graph of f double prime. So earlier in the video we saw how to do a first derivative test just by looking at a graph of the first derivative. We saw how to do a second derivative test just by looking at a graph of the second derivative. This one's going to be an example of how you can actually do a first and a second derivative test just by looking at a graph of f prime. So f prime is enough information. If we have a graph of f prime, it's enough information to sketch out a first derivative test and also a second derivative test, and then you can answer questions on both increasing and decreasing behavior, or you can answer questions on the curvature of the graph. So before we try to answer any questions below parts A, B, or C, let's just do a first and second derivative test, number line test from this graph. So this is the graph of f prime, the first derivative. So let's do our first derivative test. So we know for a first derivative test we need to know where it's 0 or undefined. So if we look at the graph, where is f prime? We're looking at a graph of f prime. Where does f prime have y values of 0 or outputs of 0? That's going to be here, here, and here. So we're going to have to estimate off the graph. So it looks like it's going to be at about -2, and then at 0, and then at probably about positive 2, somewhere around there. And the next thing you need to know about f prime is where is it positive, where is it negative. So again, we're not looking at the slopes on it, we're just looking at its overall output, its overall y value. So where is it positive? So from -3, we need to be careful with the interval here. They did say just work from -3 to 3, so we're not working from -infinity to infinity, given these directions. So from -3 until we get to 2, -2, so on this interval, notice that all the y values on f prime are above the axis, so they're going to be positive, which means f itself is going to be increasing. And then if we look from -2 until 0, notice that all the y values are below the axis, so they're all negative y values. And then from 0 to 2, they're all above the axis again, so all the y values are positive. And then from 2 to 3, they stay above the x-axis, so they stay positive. So the behavior on function f, so if we look at function f, we know it's going to be increasing, decreasing, increasing, and then increasing again. So that's going to give us the information we need for a first derivative test. And let's go ahead and look at a second derivative test. So for a second derivative test, what do we need for information on a second derivative test? Similar information to a first derivative test, we need to know where the second derivative is 0. We're looking at a picture of f single prime, and f single prime will tell you about the slopes on f double prime, excuse me. F double prime will tell you about the slopes on f single prime. So f single prime is telling you about the slopes on f. F double prime is going to tell you about the slopes on f single prime. So where is f double prime going to be 0? So f double prime is going to be 0 when f single prime has a slope of 0. So we're looking for where f single prime has a slope of 0. So if we look at a graph of f single prime, which is what we have, where do we get slopes of 0? So right here we're going to have a slope of 0, and it looks like right here we will have a slope of 0, and right here we will have a slope of 0 on f single prime. So f double prime will be 0 at those values. We'll have to estimate those values. So it looks like at about where x is -1, at about where x is 1, and at about where x is 2. So that's going to be our places where f double prime has a value of 0, because the slopes on f single prime are slopes of 0. And then we also need to know where f double prime is positive or negative. So remember, f double prime speaks about the slopes on f single prime. So where does f single prime have positive or negative slopes? So if we look at the graph, so all the slopes on f single prime are negative slopes until you get to that first possible point of inflection, that first place where f double prime is 0. So f double prime is going to be negative because f single prime has negative slopes. And then on the next interval, all the slopes on f double prime, or f single prime, all the slopes on f single prime are positive, so f double prime is going to be positive. And then you're going to have negative slopes on f single prime, so f double prime will have a negative value. And then you're going to have positive slopes, so f double prime is going to be a positive number. And remember, we're going from -3 to 3. So what does that tell us about the curvature on actual function f? That means f must be concave down, concave up, concave down, and concave up. So just by looking at a graph of f single prime, you can accomplish both a first derivative test, and you can also sketch out a second derivative test, and then you can answer any question you need to on both increasing and decreasing behavior and curvature. So here are the questions. Part A, for what values of x in the interval from -3 to 3 is f decreasing? So where is it decreasing? We want to look at our first derivative test. So we're going to look at our first derivative test for decreasing behavior. So it looks like on the interval from -2 to 0, it is going to be decreasing. Remember, we're talking about f decreasing, not the picture f single prime that you're looking at. We can't even see a picture of f right now. So this is f single prime. That's the picture of f single prime. But f, if we did have a picture of it, we would see that f is decreasing from -2 to 0. For what values of x on the interval from -3 to 3 does f have a relative maximum? So where is it going to have a max? If it goes from increasing to decreasing, that's going to make a max. So you're going to get a maximum. You're increasing, then you're decreasing. So you're going to get a max at -2. So you're increasing, then decreasing. The next one, you are decreasing, then increasing, so that won't be a max. And then on the critical number 2, it's increasing, then it keeps increasing, so that's not going to be a max. So it just looks like at x equals -2, you're going to get a max. And the third question, part C, for what values of x is it going to be concave up? So for that, we're going to look at our second derivative test. So we want to look at our second derivative test for curvature. So where is it concave up? It looks like from -1 to 1. So -1 to 1, it's concave up. And from 2 to 3, it's going to be concave up.